Okay, so welcome to the last STAMPS webinar for the spring. So we're going to resume again in the fall. So we're very fortunate to have Daniela Huppenkothen here today. And Daniela is a chief scientist at the SRON Netherlands Institute for Space Research. Previously, she was the associate director of the Dirac Center for Data Intensive Research in Astrophysics and Cosmology at the University of Washington. And before that, she worked as a Morse Sloan data science postdoc at NYU after receiving her PhD at the University of Amsterdam in astronomy. So Daniela is developing some really cutting-edge statistical and computational tools for improving inference in astronomy and data science. She's been working a lot on using machine learning statistics to mitigate systematic biases introduced by detectors and telescopes. And I believe she will also talk about this today. She's the lead developer of the open source software project Stingray, which implements commonly used time series methods in astronomy. It's quite impressive work, so you may want to take a look if you haven't already. And finally, Daniela has been very active in organizing AstroHack Week and developing new strategies for data science education and interdisciplinary collaboration. So today, Daniela will talk about unraveling the physics of black holes using astronomical time series. Okay, Daniela, do you want to share a screen?
Yep.
And
all right. So thank you very much for the invitation. It's really great to see everyone here. I see some familiar faces. So I wanted to focus today a bit on sort of the time series aspects of how we study things, especially black holes. There's a lot of things we study with similar methods, but I thought I'd focus sort of on one astronomical example, and so I hope there will be something for everyone in here. Especially for the non-astronomers in the room, if I start using like incomprehensible jargon, please stop me and be like, ask me what I'm talking about. The one piece of jargon that I want to just like explain up front, because I know I'm gonna do it and it sometimes confuses people, is the term light curve, which astronomers use all the time. And that basically just means a time series of brightness as a function of time. So often we study astronomical sources and study their brightness as a function of time, and astronomers call that light curve. And I'm trying to be consistent about saying time series when I talk to non-astronomers, but I'm not always successful. So just so you know what that means. Okay. So here's an artist's impression of the kind of systems that I study. What you have here is a black hole that's a little black spot in the middle, and you have a star. I hope there was like a star popping up there, which I can't see because of the people. And then what basically happens is the black hole is very heavy. It's very small but very massive, and if the two are sort of orbiting around each other, and if they're in the right configuration, the star will lose gas, which will be pulled into the black hole. Because of angular momentum, it cannot just simply like fall into the black hole. And so what happens is it sets into this disk and slowly spirals inward. We call this accretion disk, and we call the whole process of matter falling into a black hole accretion. Not all of this matter falls into the black hole. Some gets sort of accelerated and spewed out again in these jets. And so this whole process is really interesting because there's a lot about you can study about black holes, about sort of the principles of relativity and gravity, about plasma physics, about particle acceleration. And so the basic question we're trying to answer is, how does all of this happen? How does like matter fall into the black hole? And what can we learn about fundamental physics from there? And so there's a lot of open questions around sort of these types of sources. You know, what happens, sort of the general fundamental question is, what happens to matter in strong gravity? Black holes by themselves are reasonably simple objects, but they do quite complicated things to space and time around them. They will sort of distort space and distort time, and you can use the matter that falls in to try and study the sort of fundamental principles. One big open question is sort of the last bit, probably close to the black holes, or we know they're close to the black holes. The material that falls in is no longer on a disk, it'll be in a different sort of configuration. What that configuration is currently hotly debated. And how the jets, the sort of matter you spew out, is related to that inner flow is also still hotly debated. So one of the big questions is how these jets launched and accelerated. And then overall, you know, I showed you this fairly simple picture of things nicely settling into this disk, but that's probably not actually what that disk really looks like in practice, and I'm going to show you some examples later. And then fundamentally, what we see is light from this gas as it falls in. You can't see the black hole directly because it swallows all the light. But you can see this matter as it falls in. And so there's, you know, questions about, if we want to learn something about the black hole and the physics, we also need to learn something about how that emission is produced in the first place by the gas that it falls in. But of course, we don't see this nice artist's impression. We see more something like this. This is an image of a famous black hole. We call them black hole X-ray binaries. They are sort of binaries with a black hole, and they are usually observed in X-rays. And this is usually more what we see. And any structure that you see here is not really physical, but it's imposed by the detector. So the source itself, if you could measure it perfectly, the light would hit a single pixel on the detector, and that would be all that you measure. But because of detector optics and sort of detector effects, you get this more complicated picture. And so clearly taking a picture is not gonna give us anything useful. And so one thing we can do is we can look at the emission as a function of wavelength. Many astronomical sources emit light across a wide range of the electromagnetic spectrum, not just the visible light that we can see. And they're called black hole X-ray binaries because, well, you observe them mainly in X-rays, although they're also visible in some of the other wavelengths. And one thing that is maybe useful to know is that X-rays don't come through our atmosphere, which is good for us because X-rays are not particularly healthy, but that means we need to send telescopes into space. So all of the data that I'm going to show you in this talk comes from space telescopes from NASA, or the European Space Agency. Here, I thought I'd just show you what raw data looks like of these observations. I always find it interesting to see observations from different fields. And what we measure in X-rays is really individual photons, individual light particles hitting the detector. And so each of these dots is a photon that hit the detector. We do this as a function of time. So this is what you see on the x-axis. The gaps in there are due to the rotation of the satellite around the Earth. It has to shut off occasionally when it goes through a particularly particle-rich area around our Earth, and then it can't observe, so you shut it off. What you see on the y-axis is the wavelength of the light particles that came in. In X-rays, we measure wavelength as energy in kilo-electron volts, and it's just a sort of change around of variables. But this is sort of the raw data. In its raw form, you can't really see much more than, well, there are more photons at low energies than at high energies. And what we're going to do over the course of this talk is we're going to collapse this in both dimensions. We're going to start by collapsing it over time and just look at what the brightness looks like as a function of energy or wavelength. And then we're going to collapse it in energy and look at what the emission looks like as a function of time. And then we're going to combine the two. All right, so here's what this looks like if you if you combine this, if you collapse it over time and just look at the brightness as a function of wavelength. And what you see here is the data points as a function of energy and as a function of brightness as sort of black crosses in the background. And one thing that people have realized, you then build sort of their structure in there, and then you build physical models to try and understand that structure. And what you see in here is different types of components in these black hole X-ray binaries that make up this emission. And so what you see sort of at low energies is just this like big disk, especially the outer parts. And that's what you see as this hump at low energies. And then in the middle, this is where this hot flow is that we don't really know what it is, and we don't really know what the geometry of it is, but this is what people usually call the corona, and that produces a lot of the higher energy emission that we're interested in. And there's a lot of focus currently in trying to figure out where exactly that comes from and what the geometry of that is. And then the other thing that you see is the emission that comes from the inner part of this disk, from this corona, and that sort of illuminates this disk further out and gets reflected, and it gets reprocessed as it gets reflected, and that is what you see in this dotted line that's labeled corona reflection. And a particularly interesting feature in there that's going to come up later is this iron line, where you have fluorescent iron in this accretion disk that makes this emission. And so that's interesting. That already tells you something. All of these involve physical processes that generate light. But one thing that is also interesting is that the spectrum, this emission as a function of energy, is not constant over time. And so here you see a bunch of these taken at different times. And so there's sort of two separate types of spectra that are important. They're called the hard state, where you have emission at high energies predominantly, and then you have the soft state where you have emission at low energies. And these, so they are very dynamic systems, these black hole X-ray binaries, and they change in brightness and in spectrum as a function of the amount of matter that gets accreted. And what you find in practice is that this kind of process is cyclical. So they go through semi-regular, many of them go through semi-regular outburst phases, where normally they don't accrete very much and they're very dim. And then they suddenly start accreting more gas and they become very bright. And so the way we sort of usually encode that into a bigger picture is by taking sort of, by slicing the spectrum and then just integrating up the emission in the spectrum and then doing the ratio of the two. And so one thing you might see from this, if you sort of integrate up all the emission in a given spectrum in the purple part here at high energies, and then you divide it by the interval of the emission at low energies, you get very different numbers out, depending on whether your source is in the soft state where the soft emission dominates, or in the hard state where this high energy emission dominates. And what you find is that a lot of these sources have a sort of shared behavior, which you see here on the left. And so what these sources start out on the right, where the spectrum is very hard, and they start, so what you're seeing here is this ratio on the x-axis and the total brightness on the y-axis. And what happens is that as sort of the amount of matter that gets dumped into the accretion disk increases, they first get brighter and they travel through this hard state, and then they sort of hit a maximum brightness. And then the spectrum starts to pivot. So this high energy component gets drastically reduced, and this low energy component gets much, much brighter. And there are sort of different theories about why that is. To first order if you dump more gas in this disk, and then that matter has to slowly move inwards, and as it does, it loses energy, and that energy gets translated into light, and that's then what we see. So that's why they get both brighter, and the spectrum changes towards this low energy component where a lot of the emission from this accretion disk happens. And then it does a bunch of weird stuff over in this like soft state where it sort of moves about, and then it slowly moves back. And usually that happens over a course of weeks to months. There's a few sources that are particularly ornery who like decide to stay in this cycle for years, but in general, this sort of happens over weeks to months. Now, sort of that is a broad picture that people have been studying for, you know, a good 50 years now, and keep sort of refining and getting more information. But one other thing that you can do is you can sort of go to any of these states, any of these like orange points in there, and you say, how does the brightness change as a function of time on much shorter timescales? And so this is what this looks like. You know, if this whole cycle I showed you was over the course of weeks to months, this is now a time series in seconds, and that sort of encodes the brightness as a function of time. And this is about 1,000 seconds total. And in gray is sort of the original time series that we measured, and then I binned it for a bit of clarity. What you see here, especially in the gray time series, is a lot of variation from Poisson statistics because we count individual photons, and so you get a Poisson distribution. But then you can also see more correlated changes as a function of time. And that's then what you see more sort of when you bin it up on the blue. But that in itself is not that helpful either. And so what we end up doing is not looking at these time series, but especially for these kind of stochastic processes, what's really useful is to do that in the Fourier domain. And I'm sort of assuming that most people here have seen a Fourier transform before, but if not, sort of what you basically do is you sort of translate your time series x of t into a form, a representation of sines and cosines. And that gives you a lot of advantageous properties, especially if you have processes that are stationary over a long time. And what you then do is you take this amplitude, the Fourier amplitude, that's the sort of small aj there, and you take the square of the absolute value, and that's what we call the parallelogram. And then in astronomy, we use this particular normalization where you use the number of photons that you observed as a normalization, and that's sort of kind of useful for many of our purposes. Okay, one basic question you might ask is, well, what's the statistical distribution of that? If you assume that you have many data points, and it gets really weird if you don't, but if you assume you have many data points that are evenly sampled, so if you record it on an even grid, then these Fourier amplitudes that you're considering are approximately Gaussian. And I've tried that empirically many times for many distributions, especially for Poisson distributed data, that comes out really well, except if you have very, very few photons, then things go weird again. But if that's true, then it turns out that this squared amplitude is sort of the square of these, the sum of the squares of these two Fourier amplitudes, and sort of the sum of squares of Gaussian variables is a chi-square distribution with 2 degrees of freedom. And that is really, really helpful and makes data analysis really straightforward under certain assumptions I will talk more about later. And so here's, just want to show you, for those of you who don't like think and dream in Fourier space like I do half of the time, but what you have, you know, if you just have a constant time series with nothing in it, but in this case, Poisson distributed noise, you also get a flat parallelogram out at the other end. And usually that we also see at high frequencies where then this noise, detector noise dominates. If you now have this kind of flat time series, but you have a single periodic signal in there, then you get a single spike in a single frequency bin. And then one thing that people do very often is take that chi-squared statistical distribution that we know the mean and variance for, and you can define a detection limit and say anything that's larger than that, you know, is excluded under the null hypothesis of white noise. What I often deal with is trying to find these periodic signals in things that aren't constant time series. I often have time series more like this. This is sort of correlated stochastic variability, what people often also call red noise. And that makes sort of gives you lots of power at low frequencies. And if you're trying to find periodic signals in there, the sort of detection limit that I showed you on the previous slide is obviously no longer applicable, but surprisingly many people will still use it. But you know, these red noise processes are also generated in the source, and so they will tell us interesting things about the black hole and sort of the matter as it falls in. And then the other thing that we often have that I'm also going to talk a little bit more are what we call quasi-periodic oscillations, or QPOs. You're going to hear me talk about QPOs. These are things that are approximately periodic, but not quite. Often you end up seeing, you know, as you can see on the left hand, there's clearly something regular in there, but it varies a lot in amplitude. And if you look very closely, it also varies the frequency of that periodic signal jitters around as a function of time. I'm going to show you a different example later of that. But these are sort of the typical building blocks that we see in our black hole time series that we then try to interpret with various methods. And so just to put this all together, as your black hole X-ray binary moves through this pattern of brightness and changes in the spectrum, as I showed you, the properties of the time series that you measure at each of these points also changes. And so what you see on the right here is a progression of how, you know, the time series changes as a function as it goes from quiescence, so on the very right side, to the soft state on the very left side. And so you want to read this sort of in rows from the top left. And usually these are all periodograms now. And what you see is it starts with a lot of variability, but that variability is sort of what we call broadband variability. It's this kind of red noise. And then as this source sort of gets brighter and starts moving into this, changing the spectrum, you see this appearance of quasi-periodic oscillations. And these quasi-periodic oscillations also change in frequency as a function of time. They move to higher frequencies and they get much stronger. And then as you're in the soft state, they go away and the level of variability drops very sharply. So what you can see is it's not just the spectrum changes, but the variability also changes. And it turns out they change in correlated ways. They change together. And so, you know, the big question is how do we put that information together in ways that we can learn about the geometry and the physics from these properties? And what I've shown you so far is separating out sort of, you know, taking that raw data and collapsing it either in one direction, so you only look at the brightness as a function of wavelength, or collapsing it in the other direction and learning about the brightness as a function of time. But what we really want to do is put those two together. And I want to give you a couple of examples of how we do that. So the first thing, and one of the most informative things that you can do, is you can go back to that picture that I showed you where you said, okay, in this green part of the spectrum, you see the sort of outer accretion disk. And in that purple part of the spectrum, you see that inner accretion disk or corona. And I've already shown you in one of the previous pictures that some of that emission from the inner part of the spectrum at high energies gets reflected out. So we want to learn how these relate to each other. And one thing you can do is, instead of doing a parallelogram, you can do a cross spectrum, where instead of sort of squaring your Fourier amplitudes, you take the Fourier transform of, you know, your time series that you integrated over this area X, this green area of the spectrum. So you basically now collapse it down in energy, but only over a small part of energy, and you take the time series of that, and then you take all the photons that are in a higher energy range, and you make another time series out of that. And then you Fourier transform both of them, and you multiply the complex conjugate of one with the complex conjugate of the other. And so in this second line here, this is basically what I've written out. And I've written it out here under the assumption that the time series in Y is actually just a later version of the time series in X. So I've basically, if you assume that it is the same time series, just shifted in time, then what you end up in this sort of imaginary part of your Fourier transform is the phase shift between the two. And that you can fairly easily turn into a time lag. And so what we end up doing is we're studying time lags between these two energy ranges. And we don't just do this sort of for just a single time, or we do this for the time series, but as a function of temporal frequency. So emission that varies on longer time scales might have a different time lag than emission that varies on shorter time scales. Okay, here's what that looks like. Small disclaimer, this is actually for a much bigger black hole, but it was a really nice figure, and bigger black holes are kind of just like almost scaled up versions of some of the smaller black holes. But this is a really nice way to like, and what you're seeing here is the frequency. So this is different time scales, and then the lag between emission and that frequency between the soft band and this hard, or these two different energy ranges that I showed you. And what you can see is that at low frequencies, that lag is positive, and at large frequencies, that lag is negative. You can also turn this around, and this is now going to get slightly complicated. But you can do this lag for a single frequency range, but then you do many lags as a function of wavelength, of wavelength of the light. And this is what you see in the bottom. So on the left-hand side, this is what the lag as a function of wavelength of the light looks like for the lower, for the blue shaded region and the top. And then on the right, you can see the same for the red shaded region, and they look very different. And so that kind of tells us that these positive lags and these negative lags probably come from different processes. And the other thing that you might notice is this bump in the spectrum on the right. And this is this iron line that I talked about earlier that you see in the reflection spectrum. And so you might think, aha, so maybe this time lag that we see actually comes from reflection. And indeed, these time lags at long time scales and at short time scales do come from different physical processes. At these long time scales, what happens is that you have perturbations, you have sort of density variations that change is a function of time that starts somewhere fairly far out. And as matter spirals in, they get propagated inwards. And what you end up seeing is the lag. You see the imprint of these sort of turbulent variations as it moves in. And because things in the outer accretion disk emit at lower energy than in the inner accretion disk, you end up with this positive time lag where you see the light first that comes from the cooler outer disk, and then the other light later that comes from the inner disk. What you see at these higher frequencies is exactly the other way, is exactly the flip side. What you see there is this sort of hot inner flow. This is another like schematic. You have the black hole on the left and this a cut through the accretion disk, and then the little clouds mean to say this inner corona that we don't really understand. And that produces a time series that sort of has internal variations and jitters around, and that produces some of the stochastic variability that we see. But then some of that light sort of comes to us directly, and some of that light first ends up getting reflected in the accretion disk at different wavelengths. And so that's how you see this other time lag. What you're seeing is the light travel time between sort of the light that comes directly and the light that gets reflected by the accretion disk. And so this is sort of a way we can try to combine this information to try and learn more about the geometry of these systems. Okay. I want to talk a little bit about quasi-periodic oscillations because they're kind of fun. And these quasi-periodic oscillations are really useful for in a lot of ways, because they usually encode something happening on a regular timescale in the system. And you need to have some kind of process that can produce variations on that similar timescale. And it can often also give you limits on how big that area can be. And here's a number of examples of these kind of quasi-periodic oscillations that we see. We've seen them for a long time. And what astronomers do when we observe something we don't know about, we sort of start classifying it and seeing if we can start seeing patterns. And so the first pattern that people saw is that some of them appear at frequencies of a few hertz, and others appear at much higher frequencies of sort of hundreds of hertz. And so that's why we have low frequency and high frequency quasi-periodic oscillations. And then there's also differences between the different low frequency QPOs. And so we call them type A, type B, type C. I'm going to talk mostly about the type C QPOs. And one sort of very prominent model that now has a lot of sort of weight behind it and evidence behind it is the idea that actually this disk that I showed you in the beginning is not a nice flat disk, but it's actually warped in various ways. And so one way you can make this quasi-periodic oscillation by having sort of an inner disk that's misaligned with the outer disk. And that's what you see here. You see like the black hole as a black sphere, and then this inner little disk that's tilted compared to the outer disk. And that can happen because of certain general relativistic principles, and especially if the spin axis of the black hole is misaligned with the axis of the binary system as a whole. And then what this inner disk does is basically illuminate bits of the outer disk, and it also turns, and so you get this like illuminated spot on the disk that moves around, and that's how we can get these QPOs. And that alone wouldn't tell you that sort of people wrote down this model and they said, okay, fine, it sort of fits with the right frequency. But then the clever thing that Adam Ingram and his colleagues did is they said, okay, if this model is true, then we should see a change in the spectrum as a function of QPO frequency. Because on the left-hand side, because depending on how this is aligned and where this illuminated spot is. On the left-hand side, you have matter moving towards you. And that means that the light that you see gets slightly blue shifted. And on the right-hand side, you have matter moving away from you, which means that matter gets slightly red shifted. And people looked at this sort of peak in the spectrum that we saw earlier. And what they did was chop up the time series based on the phase it was in its QPO, and then generate the spectrum for different QPO phases for when the light comes towards you and when the matter moves away from you. And what you see here, ignore the inset, but what you see here is that indeed the red is the matter moving away from you, and the blue is at the time when matter moves towards you. And indeed, you can see that they're shifted compared to each other. And that is sort of a big sign that probably that model makes a lot of sense. And again, that required, interesting sort of combinations of how you combine this two-dimensional data set. Something that I've been working on for a long time, or for a bit, has been a source V4 for Cygni. It is also a black hole. It is actually one of the closest black holes to Earth. It's still pretty far away. It's over 1,000 light years away, so no danger, but it is fairly close, which means it is one of the sources we can actually study in quiescence pretty well. It has only been an outburst 3 times. Once in the 20s, once in the 80s, and then again in 2015. Of course, 2015 was when we had, a lot of telescopes available compared to 1989 and the 20s. And so here what you see is these are actually all time series from different telescopes. And in the top 2 panels, these are time series of hundreds or thousands of seconds, but they're very variable. And because there's days on the x-axis, it just gets really squashed together. But this is just to show you, the different types of data that we collect with different modes, where with some of these telescopes, like at the top, which is Swift, you can take many short observations, and that's great for sort of monitoring. And then with some of these instruments like NuSTAR, Integral, they will stare at something for much longer. And you can see that this source was extremely variable. And one thing that we found was sort of a faint trace of a QPO, and it's slightly difficult to see, but I can promise you I did a lot of statistical tests. It is there. And that was interesting because that was at a frequency that we didn't expect. The quasi-periodic oscillations I showed you earlier were all at a frequency more like a hertz or a few hertz, and this is actually 18 millihertz, and it's much lower than we would expect it. And what we think might be happening is actually that it's not the inner part that's misaligned, but there's some like strange warping going on in the outer disk where the outer disk is not flat, and so that's what you see there. As a lot of this analysis that I've been working on has been done with this software package that I help out with and help write, called Stingray, where we've been implementing a lot of these methods and continue to implement a lot of these methods, especially for high energy X-rays. Come and hang out with us if you need these kind of methods. We're always excited. But one thing that was particularly interesting about V4 for Cygni, I said it's very close, and therefore it's very bright. And it's actually one of the things that I find interesting about astronomy is that it can actually be quite hard to observe bright things because our detectors are all really optimized towards seeing fainter and fainter things. And so as you see bright things, you get into a lot of weird detector effects. And so, this picture that I showed you where we're like, okay, we have some time series and then we have these features and then we can like model them, that we kind of understood how to do unless our source is very bright. And for the kind of detectors that I work with, when your source is very bright, what happens is that you observe an effect called dead time. So on the left hand, this is a NASA mission called New Star. It has these focusing mirrors at the end of this large boom here, and on the right, and then these mirrors focus into a camera that's in the spacecraft on the left. And it actually has two detectors, identical ones, that record the same source at the same time. And what happens if you have a very bright source, when a photon hits the detector, you sort of measure individual photons, as I showed you earlier. But after a photon has hit a detector, you get this response curve on the right. And in this like short period, for New Star, it's about 2.5 milliseconds after this photon arrives, you cannot record another photon. So if you have a bright source, then a lot of photons are lost because you have photons arriving much sooner, much closer to each other. And so here's an example that I simulated, where you have in purple, you have the time series without this effect, and in orange, you have this time series with this effect. And if I do the parallelogram, this has a quasi-periodic oscillation in it. If you do the parallelogram, here's what you find. So in purple, you have what you would expect. You have this flat level of Poisson generated by the Poisson noise, and then you have this nice QPO. If you add dead time, you get this like very wavy structure. You depress this sort of flat noise level at low frequencies, and at high frequencies, you get this weird wavy structure. And that can mask real signals, and also makes it really hard to estimate parameters in that space. And so what you end up having is this censored Poisson process that is very hard to model in practice, because these sources show lots of rapid variations in brightness, and this effect is very much dependent on the instantaneous brightness. And so if you want to search for a periodic signal against a constant background, which is always sort of the simplest thing that you can try, and that background is very bright, but it's constant, and if you have two identical detectors, which New Star happens to have, you can exploit this real part of the cross spectrum that we told you earlier. In this case, because it's the same source observed at the same time, the phase lag doesn't tell you anything interesting, but the real part of that cross spectrum, what we call the co-spectrum, that does tell you something interesting, because this detector effect is, in the detector, and you do have two independent detectors. And if you take that real part, that effectively kind of divides out this entire weird dead time process. And so here's an example in red. This is the parallelogram of a constant light curve with dead time. This is just another representation of what I showed you a minute ago. And then if you take this real part of this cross spectrum, what we call the co-spectrum, you get the thing in black. And so as you can see, that is exactly where we expected again. And we said, cool, now we can do our sort of tests for periodic signals, except it's not quite that easy, because it turns out they don't actually have the same statistical distribution. I showed you earlier, the parallelogram has a chi-square distribution, and that only works because you took the square of a Gaussian variable, but now you're taking a multiplication of two different Gaussian variables, but they're independent, and so that ends up to be fairly straightforward. That ends up being a Laplace distribution, which I'm showing you on the left. And in practice, that's important because the co-spectrum has a much narrower distribution. And so if you use the original sort of the distribution for the parallelogram, which I'm showing on the right and dashed, you would miss lots of significant signals because you're requiring much higher detection threshold. And so this is great, but this only works for constant light curves or constant time series, and most of our time series aren't constant. So it turns out we don't know what the distribution for the co-spectrum is if you have stochastic variability in it. I recently found a paper that makes a fairly good case that it should be a variance gamma distribution, but that is still sort of, I'm still going through that paper and trying to figure out whether that's true. So you want to model this kind of stochastic variability, this like red noise processes and these QPOs and so on. And sort of on the left is just an example of how we would do this. This is data from a real black hole X-ray binary. It has a sort of bunch of feature inners that we usually model with Lorentzians. And so these are variable, and we can't, for the co-spectrum, we can't write down a likelihood. And for the periodogram with dead time, we can't write down a likelihood because we don't really have a model for that dead time process analytically that we can write down. There are some approximations, but these only work if your dead time is constant. And it turns out for a telescope like NuSTAR, it is not. And so what you see on the right is a probability density for the dead time, so how long the detector cannot record after you've recorded a photon. And it turns out it's actually quite a complicated distribution. Everyone always assumes it's 2.5 milliseconds, but it's really not. And the 2.5 millisecond isn't even the mean of that distribution or anything. So that's much more complicated than we expected. Your way out is if you're averaging together many periodograms, then everything becomes Gaussian again, and then you can use I wrote periodograms here, but I actually meant cospectra. We don't have the distribution for the cospectra, but if you average together enough of them, they will become Gaussian again, and you can sort of write down your Gaussian likelihood, and you can fit your functions and be happy. But a lot of time you might not be able to. And so for that, what we've recently been working on is sort of methods that are based on what's called approximate Bayesian computation or likelihood-free inference, or more recently simulation-based inference. There seem to be a lot of terms floating around like this. And these are basically methods for problems like this, where you're interested in a posterior probability. And in our case, what we want to know is, for example, the centroid frequency of a QPO, the amplitude. We want to know the width. We actually want to know the incident count rate, the incident flux that arrived at the telescope that we don't know. But as I said, we can't write down a likelihood. For the co-spectrum, we don't know what it is. For the periodogram, you have this annoying dead time process that messes everything up. But this...
Oh, a quick reminder, 10 minutes left. But
yeah,
I don't want to miss the spot, so just go on.
I'm done in about 5 minutes, I think. So here is basically the basic principle of how this works. For this kind of approximate Bayesian computation, classically what you would do is you would take your observed data, and then you would take your model that you think can sort of fit that kind of data, and you write down some priors, and then you draw parameters from that prior. And what you also need to do is you need to be able to simulate the process that generated the data. For that time, that's actually fairly straightforward. You can write down like a function in, less than an afternoon and generate data that is affected by dead time. And so you take these parameters that you drew from the prior and you stick them through your simulator and generate simulated data that you want to now compare to your actual observed data. And then this is exactly what you do. You compare the simulated to your observed data, and you keep parameters that produce simulations that are similar to the data. Now, the words compare and similar do a lot of work in these two statements. And there's a lot of literature around what makes good comparisons, what kind of metrics you use to compare data sets. And they're often dependent on the structure of the actual problem that you have. And also how you decide whether something is similar or not, and whether to keep your parameters is also sort of a topic of active research. The other thing that's worth noting is that traditionally, this is extremely computationally expensive because you simulate all over your prior, and then you throw most of these simulations away. And if you're if your simulation process isn't cheap, that quickly becomes unfeasible. And one of the sort of big new developments of the last 5 years or so is to combine this principle with new ideas around neural network-based density estimation and trying to sort of estimate complicated probability distributions. And here's sort of different architectures for how you might do this. You can put your neural network that is trying to approximate some of these expensive processes in different places. You can learn an emulator for the actual simulation process, but you can also learn a neural network emulator for the likelihood or the likelihood ratio or the posterior. And that's what we ended up doing, is you end up writing a neural network that approximates the posterior directly, and that turns out to be much more efficient. We ended up doing this with a mixture density network, where your neural network basically predicts parameters of a distribution. For example, you could do a Gaussian mixture, and then your parameters, the outputs of your neural networks would be the means and variances of these of your individual Gaussian components. And here's an example for what we ended up doing. So here's a parallelogram of some data that I simulated that had dead time. It has this sort of sharp feature, that's the QPO, and then this other structure in the background is dead time. And so we wanted to estimate all of the parameters of the QPO, and that's what you see in this corner plot. There is sort of the RMS is the total variance that's encoded in this particular feature, which is really hard to do in the presence of dead time with other methods. There's the centroid frequency and a measure of the width of this QPO. And then we also try to infer the incident flux that arrived at the telescope, and it was really good at that too. And one thing I learned later is that one of the reasons is why it's so good at this is that it learned the exact mapping between the incident flux and how the change of this dead time shapes as a function of incident flux. So it used that detector effect that we find annoying to actually estimate the parameters that we want to know. And so this was for simulated data, but then we also took a black hole, a really weird one, GRS 1915 + 105, it's very famous. As you can see, it has this dead time at high frequency. It also has a strong QPO, and what I really wanted to know was how does the frequency and the parameters of this quasi-periodic oscillations change as a function of time? And one thing that you can do with these neural networks, once you've trained them, inference can become really fast. And so I trained them on simulated data, and then stuck in sort of, I chopped up this time series up here into little segments, and then made a parallelogram of each one. And for each one, I built a posterior for all the QPO parameters. And so here's, for example, this is a heat map of the posterior as a function of time. So what you're seeing here is the centroid frequency of the QPO as a function of time. And in color, you see the posterior. So each column is kind of posterior. And you see that there's sort of very regular variation as a function of time that I'm really excited about, because we can now try to sort of build models for that. And you can also do that for all of the other parameters. And it was very fast. This was like hundreds of parallelograms, and we did inference in a few minutes once the network was trained. The kind of future work that we want to do, I really want to do this in a hierarchical simulation-based model. You know, I really want to write down a model for this entire, how the parameters change as a function of time, and then do this hierarchically. All of this, what I talked about, basically works on evenly sampled data. So when you record at even intervals, and we really need to extend this to uneven sampling. We're currently only doing these like very specific combinations of how time and energy, how we combine them into time lags or into these phase resolve spectroscopy things that I showed you. And I think we need more comprehensive descriptions of more of the raw data. And then future instruments will add other data dimensions than just time and energy, especially things like polarimetry. And it's going to be really interesting to see how we can combine those. And there's a bunch of future missions that, like Athena, which is going to be a big space telescope, and EXTP, which are going to provide us some of that new data for which we need those methods. All right. To conclude, I hope I've shown you that accreting black holes produce a very complex X-ray emission, carries a lot of information, but you really need to understand the subtle relationships between the temporal and the spectral properties, and in the future also between those and polarimetry. And there's lots of statistical challenges and things like uneven sampling and gaps and sort of detector responses that we're trying to grapple with. And in the future, we need both better statistical methods and also better software integration to tackle many of these challenges. And that's where I'm going to stop and say thank you.
Yeah, thanks so much for really interesting talk. So we have a few minutes for questions from the audience. And you can just unmute yourself, raise hand and unmute. I see people clapping. And Casey Mandel has a question.
Hi, excellent talk. I was wondering, hi. In your slide about the neural network emulators, what does it mean by amortized?
Oh, okay. So there are two things that you can do. Of this algorithm that we use, there is this neural posterior estimation, and there is an amortized form, and there's a sequential form. In this sort of amortized form, what you basically do is you say, I'm taking many simulations, and that's what I'm taking all of these simulations, and I'm training a neural network to approximate the posterior. And then you can put in multiple data sets if you want to, as long as they have the same priors. And they also have to have the same sort of shape. You can't like do a parallelogram of a time series that's twice as long. So it has to be the same. And that's exactly what I did for this data analysis of GRS 9015, where I showed these posteriors as a function of time. I trained this network on many, many simulations. And then I put the parallelogram in for each sort of time slices, and then drew posteriors for those. And because it wasn't trained on a specific observed data set, you can do that, but it is more computationally expensive to train. In the sequential version, what you do is you train a much smaller set use a much smaller set to train, and then you stick in your observed data, you draw a posterior, and then you use that posterior to generate simulations for the next round. And then you retrain your network on those simulations and on the simulations from the first run. And you do that sort of multiple times. And that reduces your requirement for simulations for the problem that I've been working with by about a factor of 10. But it also means that the posterior that you generate is strictly only valid for this one data set that you used in the sequential process. And so this amortized version, you just use a much broader range of simulations, but in theory, you can then draw posteriors very quickly from using the same network.
Okay, does that answer your question? I should probably add. Oh.
Well, what does the word amortized mean specifically? Like, I know it has a meaning like mortgages. I didn't understand exactly how it relates to the neural network.
Well, so well, I don't actually know what it
Oh,
means
I
in terms of like mortgages, but in terms of this, it means you can use the same network for multiple data sets to draw posteriors without having to retrain it or do like expensive MCMC.
Okay, thanks.
Yeah, it's
Maybe.
also in contrast to the ABC algorithm that Daniela showed. Like there was classical likelihood-free inference. You had to kind of iteratively train your posterior. Unlike these more modern, like recent likelihood-free inference methods, where you use machine learning methods to learn the posterior. I see a comment in the chat box by John Whelan. Amortization is equal to spreading the cost of the model training over many simulations. Is that a question?
That sounds like a definition.
No, it's a question mark.
I think I was trying to figure out if that's the right way to apply the metaphor of amortizing.
I'm not sure. I've seen Cal Kramer that was cited to use the word amortized inference.
Yeah,
and I've been using it too. you cannot save up. You save up the work you've done for training, and then you can benefit from it. Any other questions? I have a question. If I'm waiting for others. So you showed like a parameter inference for QPO. I was wondering what the parameters of interest are. You showed like around 5. And
was this here or for this one?
Yeah.
Yeah, so in the basic level, what you want to know is the amount of variance that is in this kind of QPO compared to, you know, potentially other, this time series that I simulated only has a single QPO, but usually you have more than one. And as I showed sort of in the beginning, the strength changes as a function of time as you go through the outburst. And so you want to measure how that variance in this QPO changes as a function of time. You want to know how the frequency changes as a function of time, because again, you relate that to conditions in the accretion disk. And then you often, what people also do is relate this variance to the incident flux in that QPO, and they are sort of very specific linear relationships between those. And these two have been tied to specific physical properties of these accretion flows.
Okay. Do you have about order like 4 or 5 parameters? Is that?
Well, that depends. That depends on the model. Sure. I mean, in this case, I had 4, but this was sort of a sandboxed case where I was like, let's try out this particular simulation-based inference. In practice, it can be more, you know, of the order of like 15 to 20 parameters. And there are now starting to be actual physical models where you don't fit them with sort of simple empirical functions, but you actually write down numerical models for how things propagate through, and how sort of perturbations propagate through an accretion disk. And these two have of the order of 15 or 20 parameters, but end up with sometimes very complicated probability distributions.
Are you interested in jointly estimating that many, or some considered like nuisance parameters that you want to get rid of?
Yeah, no, some of them will be nuisance parameters, but often, I mean, it depends on what kind of thing you're interested in. Some people will want to estimate sort of, you know, specific properties of the black hole, and then everything else is a nuisance parameter. But one thing that's really underutilized in this field, to the point that it's basically non-existent, is hierarchical inference, which I think ought to be more utilized, especially if you're looking at sort of this behavior throughout an outburst. But that's interestingly enough, a lot of it is a software issue rather than a sort of community issue, because the software that people use to do this kind of analysis is very, especially the practice spectral analysis, is very sort of a bit of a walled garden. So trying to bring new statistical methods in can be kind of hard.